So John, how do you pronounce your last name?
Andal.
Andal? Good, all right. That will be one.
Make sure. Right. Right.
All right, so our next speaker is Dr. Andal. Todd has an undergraduate degree in computer science from the University of Maine and is pursuing a PhD in computer science. And the title of his talk is Using Information Flow in Continual Learning.
Hello, everyone. Before I go over my talk, I want to give a brief overview about the material I'll be covering. I'll start off by addressing deep neural networks for anyone who's unfamiliar with them. We're moving on to continual learning and how it is applied to the continual learning in deep neural networks, as well as some existing applications of continual learning, existing approaches. I'll then cover the measure of information flow, which is a tool that serves as the backbone for my work in this presentation, and leave you with some results of experiments implementing information flow for continual learning and some of the conclusions and takeaways from that. So to begin with deep neural networks, they essentially serve as a nonlinear complex function that takes some input and gives an output. Structurally speaking, they're typically composed of layers of neurons or nodes, which you can see here as these circles. And each of these nodes in a given layer are connected with the nodes in the previous and subsequent layers by a set of weights. And by training these weights or tuning them, you can train the network on a diverse set of applications, including things like image classification or natural language processing. To look a little bit more deeply at the connections within the network, I want to discuss the actual behavior of the neurons themselves. So for each neuron in a layer, if you give some input to the network, they'll have an activation value A, which kind of is an indicator of their behavior with respect to that input value. Now, these activations are input value dependent. So if you give different inputs, you'll get different activations or behaviors of the various nodes in the network. And to actually calculate these activation values, what you do is for the input, or for the first layer in the network, it's based on the input value itself. But for subsequent layers, it is calculated as a weighted combination of the activations in the preceding layer. And these are used to give the activations in the subsequent layers, and that propagates up until the output of the network is eventually calculated. So once again, in order to actually train the network to give you the output that you would expect given some input, say your input's an image of a cat and you want to classify it, you would expect an output to be, oh, this is a cat. You would train the weights until the output is what you would expect it to be. So that covers briefly the kind of setting of deep neural networks. And now, before covering continual learning, I want to talk about the more broad term of sequential learning. And this is just the process of trying to sequentially train a network on a series of tasks. It has some benefits to doing this compared to training individual networks for individual tasks, for instance. The first being that you can potentially reduce the training complexity, the time it takes to train each of those tasks individually. You can store all of that information in a single network rather than several networks, so it saves on some storage capacity. And by having them all in a single network, you can share some information between the weights of the different tasks. However, despite these potential benefits, there's one kind of core issue with this type of sequential training, which is that if you have a network that has been tuned to a single task, if you try and retrain it for a new task, it will overwrite that optimization that you had on the weights previously. To give kind of a visualization of this, we have this example network, and we've trained it for classifying images of flowers as one task, and we wouldn't expect it to perform well on a different task that it wasn't trained on, such as the classification of birds. If we want it to perform well on that task, we can retrain it for that task, but doing so will rewrite the weights, it will retune them for the new data, the new task. And in doing so, you'll forget the information that you had previously learned and the ability to perform the first task. And that leads to continual learning, which serves as basically a subfield of sequential learning, where the core goal is to minimize the forgetting that's happening during sequential training. Generally speaking, continual learning methods work by identifying and preserving the information that was the most important for each of the tasks that are encountered or learned. And by information in the context of a neural network, I'm referring to the weights and the values of the weights that are learned to optimally perform a task. Additionally, other than just freezing or preserving certain weights for future tasks, you also want to be able to keep learning new information as you encounter new tasks. Effectively, what this ends up doing over the series of a set of tasks is it will partition the network such that different subsets of the weights within the network are frozen or preserved because they were useful for different tasks that have been learned. And in doing so, you can carry out the training in a way that preserves all of the useful information or the most significantly useful information that has been learned for each task in a way that the end product can still perform well on each task that has been encountered. Now, pruning-based methods are one of the most common methods for continual learning, and they're the type of method that the work I'm presenting is working with. So I wanted to go over the steps for that briefly. To begin with, you initialize the weights in the network with some starting values like you would for typical neural network training. You then take any of the weights which aren't being frozen or preserving past information. Initially, that will be all of them. And you train those weights to learn information about the new task before identifying any unimportant weights and setting them back to 0 or pruning them so that they're free to be used for any future task learning. You then freeze any of the remaining weights that were deemed to be important, and those are your knowledge that is being preserved going forward. If you have additional tasks after that you need to train, you repeat this cycle for each task until you either finish all of the tasks that you need to train for or you run out of free weights to use. At the end, once you've reached either of those situations, you end the training loop, and what you should get by the end is a network that is capable of performing well on each of those tasks that you've trained. So returning back to the concept of these connections in the network, I want to use that to illustrate to you the idea of information flow, the tool that we're using in this work. So say we have this layer where we have multiple weights or connections between pairs of neurons in each layer. What we want to do with information flow is say, okay, are there certain connections between these two layers that are more informative about the behavior of the neuron in layer L+1, given the behaviors of the neurons in layer L? So if there is one of these weights, for instance, that over a set of data, the activation values of a neuron in layer L are frequently giving some indication of the activation value of the neuron in layer L+1, you would say that there is a large information flow between those two neurons, and that is a desirable quality. So in this case, perhaps among these three weights, the first neuron is reliably across all of the data that you're looking at is giving you a good indicator of the values that are taken by the next layer. So you would say that that one has a higher information flow than the other ones. Now I mentioned that for pruning the network, you need some measure of importance for the weights so that you can pick which ones to remove and which ones to preserve. And the standard method is to take the weights which have the lowest magnitude and set them to 0 for pruning, with the idea being that if they already had a small value, it's less of a change to set them to 0 than it would if you took a larger magnitude weight. However, I suggest here that the better approach is to instead have a theoretically proven measure that is some measure of importance, and you can use to calculate the importance of the weights in the network and use that to drive your decision making about the pruning. And of course, the idea here is that we're looking to use information flow as that importance measure, and to do that, we would need a way to measure it. Which leads to my definition of connectivity measures, or the measure of connectivity, I should say, where connectivity is measuring the information flow between a pair of nodes or neurons in the network, where each neuron for a set of data has, like I mentioned, a set of activation values corresponding to those inputs. And we're looking at the Pearson correlation between those activations. So returning again to that idea that the activations of the neurons are kind of like their behavior with respect to the inputs. We're saying here, how correlated are the behaviors of a pair of neurons given some set of inputs? And if they are highly correlated, then there's a high degree of connectivity between them. So taking the activations here as being Fi and Fj given some inputs X, and conditioning over the labels of the class data, we can define connectivity here as a rho. Now, expanding on this idea of connectivity, I have task sensitivity, where the idea for this is that if you have a high connectivity, that's indicating a high level of information flow, which, as I mentioned before, is kind of a desirable quality here. It's preserving information and passing it through the network. Then it would be more sensitive to adjustments to that weight, including pruning, where you're adjusting it to a value of 0. So by identifying which weights are highly connected, you can identify which ones are more or less sensitive to pruning or to modification. And in this case, I'm looking at that over entire layers and seeing which layers are sensitive to the current task. To calculate this task sensitivity, I take the term of rho, which I defined above, and just average that over each pair of neurons between a pair of layers. So if we're looking for the task sensitivity of layer L, we would look for the connectivity of all neurons in layer L and layer L+1 and average over those to get the task sensitivity. To visualize this briefly, going back to the idea of activations, if we have some set of data that we're calculating the task sensitivity for, we start off with the activations that we receive when we run the data through the network. And then by calculating these correlations with each pair of neurons, we get different connectivity values for each of those nodes or neurons. And then to get the task sensitivity of that layer, you average over each of those neurons' connectivities. So now that I've kind of gone over kind of the ideas, the concepts that we're working with of connectivity and task sensitivity, I want to go over the results that I've gotten from running experiments with them to try and validate these ideas or verify these ideas. And for these experiments, what I did was I sequentially trained a network on a series of tasks. And when it comes time to prune each task, I calculate the task sensitivity of each layer and select the n layers that either have the most or least task sensitivity, or as a negative control, a random subset of them. Then for those selected layers, they are, every layer is pruned by some amount, and the selected layers have their pruning reduced by some percentage K. So the idea is that we would expect if the sensitive layers, the more sensitive layers are susceptible, or sensitive, I should say, to changes or pruning, that by reducing the pruning on those sensitive layers, you could preserve more of the accuracy or improve the accuracy that you see. And what we see here on the left with that top curve is that when you select the most sensitive layers and reduce the pruning on them, you preserve more of the accuracy or improve the overall accuracy across the tasks. I also look at what the effect on the accuracy is when you change the values of N and K, and see that you initially get some improvement as you increase both values before eventually, you get a drop off as you're reducing the pruning by too much or applying this method to too many of the layers. In addition to looking at the effects on accuracy, I also wanted to look at what is the behavior of this task sensitivity measure across the layers in the network and across the tasks that we train on. And so here I have 6 subfigures, each of them plotting the task sensitivity for given tasks that we've trained on, and each the x-axis for each of them is representing the different layers in the network. So what we can see here is that for at least the data and the models that I applied this to, the early and the later layers in the network tended to have higher task sensitivities, while the middle layers tended to have lower ones. And this was consistent from task to task, but raises questions for future work about whether this is consistent across other data sets or other models as well. And if so, how we might be able to leverage that behavior to improve accuracy of existing models. So that kind of wraps up the idea of using information flow for pruning the network to improve the pruning steps. But once you've actually pruned the network, you're left with preserved weights from past tasks that were important for the task that they were frozen or preserved for. But then the question is, what do you do with those weights when it comes time to train a new task? And that leads to the idea of weight sharing, where the standard approach is to just reuse all of them, to use them in learning the new task. You can't update them, but they can still, they can still affect the activation values of the currently trained weights and nodes. However, it's been shown that rather than by reusing them all, but by omitting some subset and only using the most important ones, you can actually improve the accuracy that you receive compared to that baseline. To give a brief visualization of what this looks like, say we're on task 2, we've frozen some subset of the weights for task 1, and we omit some of them now, set them temporarily to 0 for this task, and then train the new weights. And that leads naturally to the question of, okay, well, we want to freeze some subset of them, or we want to, share some subset of the weights, but how do we choose which ones to share and which ones to omit? And currently, the approaches that look at handling a subset of the weights do various forms of essentially search algorithms to identify the optimal subset by some iterative approach. Typically, these are empirical methods. They don't really have some theoretical basis or measure for how they're identifying the subset of weights that they want to pick. And similarly to with pruning, what I suggest here is that a better approach is to have some measure of importance like information flow and use that to identify which of those past frozen weights or knowledge are important and useful for the current task. And that potentially might save you the need to do these search algorithms. It might improve interpretability. And it might cut down on the computation time of having to do an iterative method. To visualize this in that previous example, say we have those frozen weights from task 1. We find that some of them have a higher connectivity or information flow than others. We would omit the ones that have a lower connectivity or information flow, share the other ones, share the ones that have a higher connectivity, and then train on the next task. So that kind of outlines the idea of how we might use information flow for improving this selection of the subset of weights that you want to share with the new task. And kind of to give it a little bit of a step back from it, the question that we're trying to ask here is whether or not you can use this measure of connectivity of information flow to select the optimal subset of weights for weight sharing. And the motivation is that if you could do this, you would have some information-driven metric that rather than being this iterative search, you would actually have an intuitive decision-making process that depends on the behavior of the network with respect to the task at hand. And that could help drive future methods and help improve the overall, again, interpretability of these methods. So the actual underlying kind of hypothesis behind why this might be feasible is that if you are training on a current task, say task 3, and you're deciding which past frozen weights to share or reuse for the current task, if you find that the behavior in the form of the connectivity of the frozen weights of, say, task 1 are highly similar to what they are for task 3, so the same weights have a similar behavior as they do for the data of task 3, then you would expect that the tasks themselves are similar because they are evoking similar behavior of the network, or that subnetwork, I should say. And if the tasks are similar, then the weights which were initially frozen because they were useful for task 1 would be expected to be useful for the more similar task, current task at hand, task 3. And by sharing those weights, you would expect that you can avoid the need to learn any redundant information that they might confer that's useful for the current task. So I've run some preliminary experiments on this, and the idea behind them is that I wanted to see for similar and dissimilar data sets how these connectivities behaved. And to do this, I broke down 2 existing data sets into 4 subsets: small animals, large animals, trees, and hand-drawn digits in the MNIST data set. And the idea was that I wanted to train a network on these small animal images and then evaluate it on each of the 4 tasks and see how the connectivities compared between them. And so in doing this, what I did was I calculated the connectivities of the network on a given task, and then took the average squared difference for each weight's connectivity across the entire network. And my observation was that the similar data sets of small and large animals had the least difference in their connectivity values. meaning that the behavior of the network was most similar for these similar tasks. Whereas small animals and black and white hand-drawn digits, which would be the most dissimilar, had the largest difference in their connectivity profiles. And these give a promising and a first look at a comparison of connectivity and performance, connectivity and like network behavior for similar and dissimilar tasks. But going forward, it's going to be important to establish some proofs and complete those for justifying weight sharing based on these connectivity values. After which, setting up and running some experiments to verify those findings, those proofs will be necessary. And ultimately, the goal will be to design and implement some continual learning method that leverages these connectivity values and information flow in both the pruning and the weight sharing of the network. Thank you.
All right. Here. Sebide, any observations about the slides?
Will you go to slide number 2?
This one there.
Yeah. I think it's a personal opinion. I think if you had some bullets when you bring each line, I think that would be easier to separate them, And also in slide 4, number 4, you have written a new task. Problem.
Oh, okay.
If you go to slide number 9.
This one?
Yeah. Again, it's a personal opinion. When I wanted to present your project, I used 20 minus K person. And I found it easier to figure out what this K person means. You know what it is?
Yeah. I say like here's the baseline
Exactly.
and then minus. Yeah.
Yeah, exactly. But other than these, that was great thing.
Then
Yes. Next presentation is the talk on continuous speed and flow. And he used the sans serif font in the topic.
that was one of my points, yeah.
Yeah.
I think the sans serif perfect for papers that you write, for thesis and so on, or anything that is projected through the digital.
So question, because as I mentioned before, I am font blind.
Oh, okay.
So I assume sans serif is a family of fonts, or because I used Times New Roman for it, and I thought the issue with the fonts before was that I was using inconsistent ones, so I just set everything to Times New Roman.
Okay.
Did I pick the wrong one to set everything to?
Exactly.
Okay.
Just look.
It's
at-
consistently wrong
Yeah.
now.
Look at Arial
Yeah,
or
okay.
Helvetica
Okay.
or one of these fonts.
Yeah.
They don't have these tiny things.
Yeah.
You did it
I
perfectly.
did get the sense, I was like,
because-
this feels very typewritery for a presentation. I didn't
Yeah.
know how to put it exactly.
No, that's,
My
I
thoughts.
agree, but
Okay.
these here, since they have these tiny things added, and you have pixels, yes, there is dithering here and there's, and all that stuff.
It's like
Prove
Arial
it somehow, but it's a little bit gray.
So Arial's a safe bet for just,
Yeah.
when in doubt, just set it to that. Cause that's what some of it was, and then I was like, oh.
Okay. Otherwise,
Thank you for pointing that
Yes,
out.
sorry. Other one point is once appearing the one bullet point, it's only appearing the text. Empty, the slides are white space. And we have to read the complete one sentence. And if you merge with some images or one bullet point and one image, then it will increase the visual appearance. While we are talking, only we could see one bullet point.
Are you saying to introduce the images like after a
images
bullet
and
point?
for the corresponding images for that point,
Rather than
Yeah,
like do all the
yeah.
text and then the
Yes,
interviews.
yeah, image.
Okay.
I think that's a
That
good
makes
suggestion.
sense, yeah, that was a little bit of me being lazy, but yes,
Yeah,
I will do that for the next iteration, thank you.
Thank you. Yeah.
Time wise.
Was it a
We
little
can
bit long?
condense it a bit, it was 23 minutes, so the speed was, okay, you were stumbling at the beginning, there was.
Yeah, that first slide is
Something
bad.
didn't go perfect there, but you caught up with that and it went well, you had good gestures, it felt, since this is full 20 minutes, it felt after a while that it became a bit monotonic. So feel free at one point to just stop and take a break for not a minute or something, take a break and then start again and use your voice to have that modulation in the whole thing. And then you see, you will get a better connection with the audience.
Do you think maybe between like the part that was about crooning and weight sharing, that
Or
would be a
it's,
good,
yeah,
like.
right, and think yourself, are
they?
they something like 3 parts in your major parts in your talk that you can have twice that pause in it, that allows everyone to reboot, and then you go and do the next thing. Often, at least in the beginning, several times, you come to the next slide and you were building then a bridge to backwards to what you just said. And while this can be useful, I think it was one of the reasons why the talk extended. And I think you can be faster there.
Like the transitions between slides, like make it a little bit less repetitive or something like that.
Exactly, yes. You use such words as "to begin with," and maybe you can be there more precise, something like, my work is about deep neural networks, a research topic which is within the contemporary area of AI. All right, so gives a little bit more and avoids the kind of the relatively empty "to begin with" statement. Can you go to the sequential learning slide? This was relatively early.
Yeah.
Yes, here. And can you do it full screen?
Like the presentation, like slideshow animations.
Good. I was wondering whether the benefits, rather than having verbs there, to convert that to nouns. Because if it has, the moment you start with a verb, you're introducing essentially a full sentence. All of us will read that completely. You did not do a slide reading. You were very good at that, and I don't want to go there or try to criticize, but I think it would be, and it's and it's parallel that you have the verbs always at the beginning. That's fine. But
something like lower training, like less training complexity, less
training or reduced training complexity, less overall or smaller size and shared knowledge.
I think I like the verbs better if instead of benefits, if it was like sequential learning and then verb. If it's like a noun at the top rather than like something unrelated. If it fills out the sentence, right?
Just an observation.
Yeah, I think it makes sense.
There, I thought on that slide, the figures worked extremely well. Also, how you explained that, I really like that. Next one is, I think, on continual learning. You have the acronym CL, but you're not using it. At least not on that.
I use it down here.
Down there.
I could make that 2 lines and get rid of the acronym and just.
Maybe something like that. Yeah.
Yeah, because I don't like having it.
There, the ors between your figures, they looked as if the text is distorted.
Yeah.
right? It's scale, so
I can replace that with the correct
With
font and.
regular
something that's not
sized font,
distorted,
I
yeah.
think that would do better. There's a, oh yeah, go to the next slide. There was something in the animation where you jumped ahead and then it went back.
Yeah, at the beginning, I think I skipped to the second box. so
See,
that- Yeah.
yes, right. So to see that it's always going forward. The thing that I believe here, if you kind of, finagle that a bit, such that you start with the at the installing weight with a red line, you go out and you don't have yet the incoming one. Right? So that it goes into the cycle
Like part of the way.
part, and as you now continue, you will see that, and then afterwards you have that arrow that goes off, that's fine, but you never close the loop.
Yeah.
And it is as if there is the constant gap. So you would want to have maybe at the end, the arrow that moves then to the beginning to have the full cycle, because you said, or alternatively, one goes again through that hole.
I see.
Stuff, right? So avoid that gap there. The information flow slide, I think, which is the,
Sorry, because I'm just
Yeah.
thinking about it, like, looking at, does this look off center to you when I can't, I feel like I must have centered it, but looking at my screen. it
it's
feels
not
like-
centered.
Okay. I will look at this. Something that, yeah, it's odd, because like Google Slides has like the centering
Oh,
lines and stuff,
yeah.
and I was like, sure, I did. But there's no way that is, sorry, do you say information
Yeah,
flow stuff?
looked text heavy.
Okay.
At least to me, and I thought, could you
I think I can probably.
write up
summarize
the
the second
first
part.
bullet or I don't.
I think I just
Just think about
combined the second, like existing methods are approached.
Maybe I was actually thinking about the next slide, which also, that also have.
The next one's
information flow?
it's measuring information flow.
Ah, this one, yeah,
Right.
measuring information flow. There, I thought actually, maybe it's beneficial to have information, measuring information flow and only the connectivity on the slide, and then have another one, only the task activity or whatever.
Because we had discussed it a little bit in the
okay.
last one,
Yeah.
and we were kind of on the fence about whether having like the red highlighting and showing
yeah,
the.
I think the red highlighting is on this time, it worked. I thought it was a bit dense.
Yeah, if you still think it's a bit dense, it sounds like maybe I should just.
The
let it
alternative
do.
could be that you leave the two items on it, but don't squeeze the example onto the same slide, but have a separate one for the slide,
Okay.
for the example.
That would be doable. I was just thinking like, cause if it was connectivity and then task sensitivity, like with the example or something, it's like. It's a trade-off between having the parallelism versus having space on the slide.
This is up to you.
Yeah, I think that was a good idea.
The next one I think is results. And so what I noticed here, you have results of experiment or something like that. And later on, you come with preliminary experiments as the heading.
Yeah.
So,
Well, it's the preliminary for the weight sharing part, whereas this
Okay,
is
so
results from
here we
like
go.
previous
So
work, kind of, or
maybe
previous
it is
results.
results of, and not of the experiments, but what did you actually
I see.
test here?
Yeah.
Then preliminary becomes, again, results of weight sharing.
Like results of like connectivity on pruning or something.
Exactly, you're right, because to me, it sounded like, okay, so here are the results. And then a few slides later, oh, there's the experiment. How can the results before
Yeah,
running
that makes
or
sense,
before describing the experiment? Let me see. Okay, the slide where you have the 6 graphs here, you said, we see. And I didn't see anything.
So,
And there was something about the middle sheet, or middle, I don't know what the noun was, and it wasn't clear to me what. Yeah.
Where it shares both axes.
Exactly.
Yeah.
So, maybe, although I said, okay, be shorter, but maybe spend time on one of these, maybe larger,
Right.
and then show all 6 of them.
Okay, that is a good point. Like have one blown up and then maybe build them sequentially
Yeah.
after I've explained what they're looking at, yeah.
And then there was the one with the slide with the table at the bottom. Yes, and I think you can improve here visually by not having the outer frame.
Okay.
Just the, certainly you need the horizontal lines, probably the 2 vertical in the middle, but not the entire thing around it, and it will be a bit lighter.
Yeah, like a paper style table.
Yeah.
Okay.
And otherwise, it, I think same as with before, a conclusion slide. Before future directions.
Okay.
And then, yeah, also think about how you can avoid a sudden death on that. That's a charge for everyone, always the hardest piece, and you want to avoid this typical question mark slide where so many people are using. You have to see that you find something personal there. Ideally with respect to your own topic, what you're talking about, and you will see it, it makes a difference. Otherwise, well done.
I have a tiny comment in the previous slide. Maybe it would be better if you reduce the white space in the table.
Oh, yeah, like at the, up here.
Yeah, in the where small is written, or I mean the column. Reads.
I also realized I copy pasted new values in here and I forgot to. I'll release on my own. I forgot to recenter them. Thank you for all the feedback.
All right.
By the way, do you want these uploaded to Dropbox or is this happening? Okay.
All right, so our last speaker is Sanendran. Sanendran holds an undergraduate degree in surveying engineering from University of Sri Lanka. He is a Fulbright student and he is pursuing a master's in spatial information science and engineering. The title of his talk is Areas of Same Cardinal Direction.
Thank you all of you, and good afternoon. And today, we think about the human conception in the defining the direction relations. Just we concern our room, and I can observe these things, and where is it? And as it is, I can observe it. And once I communicate with others, I can define it. Yes, that's my laptop is placed on the right side, and the tables are in the left side, and these kind of things, I'm using the qualitative direction relations to define the connections, the relations between the objects and me. And simultaneously, when I went to the outside of the space and the geographic space, we are observing the extended objects. And there are a lot of objects, and we want to define the direction relations. Once I'm capturing it, does not need to share with others. If I want to inform, these are the direction relations, and here to the Fogler library, what are the direction relations? So we have to direct them, and there should be a one common reference system, and that's commonly we are using the cardinal directions. It means north, east, southwest directions, and that's a compass directions. We are using that one and compass. just we think about the geographic space and what are the queries we could ask. From this one, this is the one projected map of United States and Canada, and we want someone could ask the query, what is the direction relation between the Canada and the US? Then typically we can answer that United States south of Canada, but in this case, it especially if one in the main can't say I am south of Canada, that the same answer could not apply to these wherever in the main. And is main, it has north, east, and the northeast and the southeast part where the Canada regions. So then there are several models we are talking about using to define the direction relations. First, we are introducing the point-to-point direction relations. And the first, the extended objects, they assume that approximate that extended object into the point-like object. And the first, the triangle model introduced, and it captured the direction relations. And next, the ground-breaking one model. It's a projection-based model. It introduced the 9 direction relations to define the point-to-point direction relations. These are the 9 atomic relations we are using this one, and how it applied to the real-world applications. Just if you want to define the direction relation between the Hurricane Ian and the US, then we want to use this model, and it concerning the approximate locations. Then using the United States, you are considering the centroid of the United States, and simultaneously you have to calculate each moment of hurricane points, and then only you can define the direction relations. But here we are approximating the extended object into the point-like object. Then the region-to-region direction relations. Here they're trying to avoid the approximations to the point-like approximation, and they're concerning to preserve the geometry and the shape of the objects. Then the region-to-region direction relations, and the first and the direction relation model we introduced, keeping the target object shape, and they're approximating the reference object into the minimum boundary rectangle, and based on the reference objects approximations, they're partitioning the surrounding environment into the 9 cardinal direction tiles. And what are then once the target object falls into the reference area, it defines the same direction values, and simultaneously there are different configurations. So we could have the target object completely fall into the reference area, then it shows the same results, but still we have the direction relation between the target and the reference area. Once we apply this model into define the direction relation between the Hurricane Ian and the United States, once the Hurricane Ian moving through the south to the central neutral zone, then south part of the tile, it defines the directions. But in the central part, and once it to the neutral zone, we don't have the directions. That essentially to show that it has a neutral value. Once this concept leads to think about the cardinal direction as a field, that every locations we have the direction relations inside the neutral zone and outside the neutral zone, and every point locations we have the directions. We can define the directions, but it's continuous. Like a temperature, we think about the temperature, how this field going to be work. Temperature maps is providing that each locations it has a temperature value, and we can define the temperature over these any locations. Simultaneously, then we're concerning the cardinal direction as a field, it exists everywhere. And from the target region, it's a exterior of the space. Anywhere from the exterior, you can define the cardinal direction. It's a continuous and exists everywhere. Now, we're using this projection-based model. This basic is a projection-based model, and projection-based model concerning the point reference. That simultaneously, we are using this point projection-based model to define the point to region directions. The point to region directions meant that then reference, it's a point. That's important. And the direction relation matrix, it uses the reference as the area. Then what are the differences? It's that the direction relation matrix considering the reference is MBR, and the point reference model, it's considering as a fundamental unit as of a point. It defines that how to define these point to region directions. The symbolic representation capture these point to region direction relations. Then what are the realizable point to region relations? The point exists everywhere. It's an infinity. Then infinity direction relations, we can define it. But we need the finite set to define these direction relations. Then that 9 elements, then we organize the 9 elements, and 9 elements it yields to 512 configurations, different configurations. And from 512, these 106 unique elements, it shows them, and these are the available through the exterior of the space. These are 3 consistency constraints define these 106 elements. These 106 elements, under the 90-degree rotation and mirroring, it introduced the 22 normalized relations. You can consider these 14 relations. It applied to define the 4 additional relations in the set, and the rest of 6 relations, it generated the 6 considering the 90 degrees and mirroring concern, and 2 of them, they don't use the 90-degree rotation and mirroring. Using this concept, we tried now we reduce the reduce the possibilities 512 to this 106 and 106 to 22 atomic relations. These 22 atomic relations wants to be organized. When where is it? How they are connected? These kind of things we try to identify, and the reference point, it applies the deformations. Deformation meant we change the location over the exterior of the space. And while changing the locations, how these direction variations are going through. And we are talking as it's continuously varying along the space and from exterior to target. And simultaneously, we use the union and intersections for between the atomic relations. It shows the relationships, and it allows to order the base relations, atomic base relations. And these atomic relations with the 22 atomic relations, it introduced the conceptual neighborhood graph. This conceptual neighborhood graph, it organized based on the relations, and it follows the intersections and unions. It has a connections in minimum the relations has 2 connections with and maximum the relations have the 5 connections. And simultaneously, there is a 90-degree rotation and horizontal mirroring and vertical mirroring. Using these compositions, we identified that the 8 different set of these 22 configurations. Then it allows to identify the conceptual neighborhood graph for 106 elements. And these are the 2 layers. We introducing these 2 layers. And the first one is consisting with the 53 elements, and the second layer it takes 53 elements, and each relations connected with the center element. And this configuration, this is a conceptual neighborhood graph for 106 elements. Through this one, and next is a very brief introductions to areas of same cardinal directions, and now we are going to define these region to region direction relations. So now, last we talk about the point to region directions. Now we move into the region to region direction relations. Using this point relations concern, here we are concerning the regions are point set, and the reference is a set of points. This all the regions it's made with the set of points, and a reference region would capable to have the single direction relations. If it's fall into the one direction tiles, and it capable to capture the one direction, and sometimes the reference region could have the different multiple directions. Now we have to partition this entire space. We have the finite set of element relations to define the direction relations. Now we need to partition the exterior of the target object, and this leads to the first tiles of same cardinal directions. It allows we constructing through the extrema points of the target object. The extrema points mean that the object it has a extrema, it's absolute extrema points in the northmost and eastmost, southmost and westmost. And in this region, we are using the projection based model to define partition the exterior of the target object. And following we are using the swept line algorithm and assigning the cardinal point to region directions relations for the each tiles. Next, the inside of the target area, we are considering the pockets of same cardinal directions. These are not the rectangular tiles, these are the pockets. It will depend on the shape of the object. It proves that yes, we are concerning the shape of the target object. And here, especially we are defining some local extrema points and split lines, and we will detailedly talk about this process, how we are going to generate it. The tiles of same cardinal directions. The first, we are defining the extrema points. Through the extrema points, it's constructing the bounding box for both reference and target objects. Using these bounding box, we are defining the vertical split line, and vertical split line while passing through the target extrema points, it defines the left and right tiles. Through the left and right tiles, once the horizontal split line passing through the northern extreme point, it again split the top and bottom partitions. You could understand, you could see that one, the vertical split line and horizontal split lines. They have the both configurations, that the horizontal vertical and horizontal bottom. And they have the different configurations. And it defines the 8 direction tiles around these exterior. In this, it has a unique cardinal directions. Point to region cardinal direction is showing the point to region cardinal directions. And from this exterior space, the 16 base relations we are using to explain this exterior of the target object, we are using only the 16 base relations out of the 106 base relation, and the 3 normalized atomic relations for the disjoint target area. So you could easily identify these things from we are minimizing the finite sets with and neighboring graph, that how these 16 relations are connected in the neighboring graph, neighboring graph. That's important. And how these connections are happening. You could say that that red circles indicating them how these extrema, if you are taking some points in the extrema, how they are following. They have the real connections between the relations, and it's showing that they are the base for in the conceptual neighborhood graph, and the 16 relations. Then, if you are missing some values to continue the to represent the continuity, then you can pick the relations from here. Then it allows us to interpolate the cardinal directions. New concept to the interpolation about the directions. Now we are moving the inside of the target object, and it's completely depend on the target shape. And here we are defining the pockets of cardinal directions, same cardinal directions. And here first we are defining the local extrema points. And for the local extrema, we need the vertical and horizontal split lines. These split lines, it captures the one of the vertex and region along these along the axis, and it defines that if the vertex and the interior of the region are disjoint, it introduces the local extrema. Then it defines the pockets, and there's showing that how these vertical split line and horizontal split lines are working with to define the pockets. Sometimes the both pockets can have this common region. That common region could have the one separate point to region relation from 106. And in this case, we introduce a 1 point and a V3, and it's not a local extrema. It's a sample for this one. And these pockets for this for the how these pockets are available through this region, and this for this example, it's showing some pockets with its unique cardinal directions. One advantage of these pockets is the number of pockets are not very with only it's depend on the shape of the object. If you are using the continuously one target object to define the relations, it's constant. Number of pockets are constant for the particular target object. Once you calculate the number of pockets, you can keep it as a reference. And the direction relations are neighbors of how these. And now first we consider the how there's tiles are related in the neighborhood graph. Now we are concerning what is the relation between the pockets. That simply you could see the pockets are surrounded by the areas, the target region, and some other pockets. Now we have to understand what are the connections available. Could we implement the conceptual neighborhood graph to explain these connections? Yes, you could do. And these connections are established in the conceptual neighborhood graph. Continuously flows your points along the pockets and the interior of the pockets while you are passing through the other pockets and the neighboring pockets. Then you have the connections. And every connection, it allows to find some direction relations. You don't need to identify the R1 to R9 continuous directions. If you want the continuous directions, so you can follow the direct path in the conceptual neighborhood graph. And the conclusion, the point to region direction relations, it introduces the 106 base relations out of 512 combinations. Now we have the fixed finite set of direction relations and 22 atomic relations. These 22 atomic relations capable to construct the rest of 106 elements. under the 90-degree rotation and mirroring. These ordered relations construct the conceptual neighborhood graph. There's a conceptual neighborhood graph allowing us to interpolate the cardinal direction relations. Then it allows to introduce the region to region direction relations. These all the concepts are not following any approximations. We are just treating our extended object as it is. This region to region direction relations is introducing the areas of same cardinal direction, and the tiles of directions is introducing the 16 base relations and normalized into the 3 atomic relations, and pockets approve the conceptual neighborhood graph relations. And these few concepts, it leads to the next future work. The future work, how does it work on the surface of the sphere? Now we discuss and we introduce this concept on this projected surface, on 2-dimensional surface. How does it going to work in this surface of this sphere? So we are concerning our Earth, it's approximated as a sphere, and so how does it work to the sphere, and how we are going to construct the projection-based model into the sphere. And in the same relations, we can apply it here, point to region direction relations, and simultaneously that 3-dimensional space. Once we are concerning the 3-dimensional space, how we are going to define the direction relations between the volumes. These are the future directions, and if you have any questions, you can. Thank you.
All right, thank you. Josh, what are your thoughts?
How was the time?
I'm just looking, 23 minutes, so.
It's not that it felt like it was too long, but it felt like it was a lot of information.
Tons of stuff.
Yeah.
Yep.
Which I don't like, it seems like a lot of it's important information, as someone who's less familiar with the field, it's like, I hesitate to say like, oh, cut stuff, it's like, it's
I
easy
agree.
to say cut stuff.
Yeah, I think for the 20-minute talk, there is ample opportunity for eliminating some things that are not really needed. And by streamlining that, I think it will benefit.
I'll say the things that stuck out to me, maybe, I feel like maybe if the focus is largely on, you know, being able to incorporate kind of describing these pockets in the model that you're using, and like, connections between the different, mixing up my terms, be like the connections between the different relations, then maybe you could probably get away with fewer of the introductory slides describing different types of models. One thing, can you go back to, I think there's an early slide, I get, again, the terms I get mixed up a little bit, like I think it's DRM and the point reference model, it's like probably the 5th slide. Yeah. Or even I think the 2 after that one, I think. So when I was reading your manuscript and like preparing this, one of the things that stuck out to me, and hopefully I'm understanding this correctly, is when I was kind of navigating the figures, and you had like what are the relations if something, if a target is like in the diagonal, kind of like corner square, versus once it crosses a line, I kind of realized like, oh, it kind of, the lines are point based, it felt like, around the axes of the corners of the bounding rectangle. And so if that is the case, if like the point based, it kind of feels like the region that you have, the middle is that minimal bounding rectangle, and then the corners are point based for determining like when something's crossing over a line. If that's the case, maybe having something where you show both of them in the same figure where it's like you have that corner of the bounding rectangle, like here would be a point.
Yeah.
And here's how we're describing everything from there. That might help connect the idea a bit, if that is an appropriate representation of what you're doing. And then can you go down to where you have like the graphs, starting with the one that's kind of like this wheel of the expanding, well, this was in the previous one. In the previous one.
Yeah.
It's hard to suggest this with the being a little bit over time and telling you to cut stuff. But this one, I felt like if it's an important concept to develop on, it seems like it might be related to where you're talking about connections between different relations later on. Maybe breaking this down so you're showing what each of the colors represents. Like, why are two connected ones that are connected with green related? Why are two connected with pink related? And then build out, okay, now that we've defined these types of connections, here's like what the whole graph looks like. But that adds a bit of time. And I don't, at this point in I guess it's slide 9. So it shouldn't necessarily be hyper specialized, I guess. But I think it would be better interpretable if you did something like that, if they are color coded in that way.
Yeah, I thought that slide would be ideal for developing it iteratively. If you start, for instance, at the bottom left, where you have just the northwest corner, and then you say, okay, the most similar configurations are if either the center tile is added or if the north tile is added. And that continues, and then it's always, as you go along an edge in the graph, you always add exactly one additional tile. And that is the rationale for getting this graph here. And if one then analyzes that graph, and now you go onto the right-hand side, you see that then there is a very consistent distribution of the cardinality of the nodes. Something like that will make it easier to get through this material here. Yeah.
And as a kind of a catch-all for the rest of it, like from here on, the only kind of things that popped up where it, because you have so many different like representations or relations, then the figures just become kind of large. And when you're talking about the connections between them, I imagine it's beneficial. You probably, it seemed like you need to be showing them all to show where the connections are. If that's, I don't know if it's a common graph that like people in the field will recognize it and say, oh, it matters that the connections are this bottom row versus the top middle, or but if it matters, then I would show the whole one. If not, I would see about simplifying it and not showing as many of the unrelated ones. Yeah, like here, like you're just showing along the bottom row, but I don't know if you need to show the top half of that, or if there's some way to abbreviate the visuals a bit.
I think here, and when I saw it first time, I was wondering, what are the blue ones versus the black ones? And then I read, oh, the blue ones are the ones with the center tile and the black ones without the center tile. And I thought, oh, but maybe this could also be presented iteratively, that you show only the black ones connected without the blue ones, and then you say, oh, but we have 53 and 53 without center, 53 with center. Those with the center, you take away the black ones, they form the same shape. If we bring them together, however, we have a really complex network here, but it is still less than if this were a complete graph, in which case you would have, you can calculate how many edges there would be in a complete graph. You have here only, you count how many edges you have. This is a significant improvement in reducing the complexity of what potentially could be there. So, something to that effect. Don't need to write in your thesis about it, but in the presentation, this I think this could be very effective.
And that was the last thing I was going to say is it feels like the most I feel like I may be spitting in the face of the field saying this, the most trivial to understand of the connections is when the center dot is, when it's overlapping, I guess, that center point. So in terms of visualizing it, I feel like as someone who's not super familiar, as long as I know what that center point being filled represents, like Max was kind of getting at, like, it feels like it just doubles the amount of visual information when you include that. Like when you have the two, where you had the two, like you're building out like kind of like circles, concentric circles of relations or whatever. And you have one half of it is without the center and one half is with the center. And like there's an arrow along the bottom that's just the center being filled. And it's like, I think that's maybe part of the idea, is that it increases the amount of representations by a lot, but visually it also doubles the amount of clutter unless it's really necessary.
And yet again, another opportunity for probably doing it iteratively. At first, here are the 53 without the center tile. Reason without the center tile is none of the target object extends exactly up to that the origin. If that were the case, then we're getting, take those away, we're getting those 53 over here. And of course, they are highly similar. Bring back the original one, because in essence, it's a copy with filling in the center dot. Something to that effect will make it lighter.
Yeah.
This graph here showing 106, that's a lot.
Yeah.
Right? So you want to show that and initially I thought, oh, don't talk about the normalized stuff and so on, but now I think hearing your feedback, I think reducing it from 106 to down to 22 or whatever it was, the number is, I think that's significant insofar as it reduces clutter on the screen.
Yeah, I think it was good, and I liked all the figures. It was clean to like the visuals. You know, other than like clutter and figures like this, where there's a lot of data, it felt well presented and everything. And I lost my train of thought. But yeah, no, I think that, like you said, building iteratively and kind of explaining the concepts and then introducing all of the information would be really a good step. It's kind of a case of less is more, I think, also in some of it. Yeah, thank you.
Yeah, thank you.
Seconded, you had anything to add? Any additional observations?
Actually, the first thing I have to mention is that they don't have any slide number.
Yeah.
So I couldn't address which slide I wanted to talk about. Other than that, the animations were really helpful, especially for the pockets and everything. But one thing that I was wondering is that which part is description of some known or standard definitions and which part is your method, you know what I'm saying? I couldn't separate which part was your method specifically.
I think that's exactly what I wrote down. I wrote that I think it needs 2 explicit slides on previous work or related work.
Exactly.
And so that it's introduced. I think you need the Andrew stuff, you need the Papadia stuff, you need the directional relation matrix and without all the other clutter, without the Hurricane Ian and so on, just these methods there, and you are building on what Andrew did, and you're comparing it with what Roop did and what Schneider did, for instance, right? So something to that effect, and then it makes very important also for thesis writing and so on, that you clearly get what others did, you get that out of the way, and then later on, there are almost no further citations needed, because it's clear that this is now your work. And so that's how you want to present it. All right, I have more detailed notes here. I'll share them with you privately, but otherwise, a very visual talk. It's a very visual topic. Also, you're making very good use of it. So I think it goes in the right direction.
Just another comment I had is that I presented your work and
Yeah.
I know what minimum boundary rectangle
Yes.
is, so I saw it on early slides, but I saw that you define it afterwards, so
Yeah.
I think if you define it on the early slides, it would be better to understand for the audience.
Okay.
But it was great.
Thank you.
Good.
Sorry, just remind me, like one thing, just something I did really like, I think it was the slide you were just on. When he was mentioning kind of maybe cutting some of the stuff about Hurricane Ian or, you know, moving it or something to declutter. I felt like you probably don't need, like, it felt kind of like a motivation or like trying to make an application for the work to justify it or something. I felt like it's interesting because it's so visual as an audience member. I found it interesting enough without needing like a real world example of it in use. I don't know if you agree that it needs that. But like seeing the target move around and how it affects the like, oh, the model is useful, oh, up until you put it in the minimal bounding rectangle, and then it can be in different spots and it gives the same relation. I felt like just seeing that kind of, you go through that was interesting enough that the Hurricane Ian stuff didn't feel necessary to make it interesting. It kind of maybe added to some of the length of the talk or something that you could trim down. Just as an idea of things that you could maybe cut. Yeah.
All right, good. Let's wrap this up. We're way over time. But
Sorry, I contributed
no,
that,
no.
I'm sure.
I think it was probably a very, very good, well invested time. And I appreciate what you did. Very clear progress compared to when we saw the slides before. And every one of you well presented. So I'm very confident that we'll have very nice seminar talks. The talks will be over in the other room, so probably at one point or another, familiarize yourself with the room when no one's there. There's a punch code you can get from Karen. You can get the key combination, just that you know how to start it up, how to connect and just stand there. It's a little bit different from here. My old story that you want to go into the room where you present at least the night before, so that when you come in, it's not, oh, that's totally different than I thought, or it's reassuring, and when you are convinced of yourself and everything is fine, the talk goes much easier. So, all right, next week is posters. Did we say draft ones? Yes. So draft posters, which we will review, and you will take into consideration feedback that was collected last week, and well, we're well on our way, and next week we will certainly be in April already, which is a clear sign that we are wrapping up here. And yes, you have been very busy with this course. I understand this is a 1 credit course, much more work compared to that 1 credit. But on the other hand, I think you're getting out of it something that it really will pay off. And the closer you have your topic to your own thesis work or so, you see how much you can reuse that experience or reuse slides. And I hope that all works out. Good. All right. See you guys next Friday.
So is this the last time you're rehearsing?
This was the last rehearsal of the talk. Yes. No more talk rehearsal, because next week is the poster. Then one Friday is the actual poster presentation at the graduate symposium, and the Friday afterwards, I believe, is already the seminar talk.
Yeah.
So it's very, very fast as we're going towards the end of the semester.
Yeah.
Also because you have so many things to do. So
Exactly, yeah.
if you have nothing to do, oh, it goes slowly.
Yeah.
But
Exactly.
good.
but
Okay, enjoy the weekend and we'll see you next Friday.
Thank you. Did you say you recorded that on your computer or is it recorded on that one on your laptop?
it's on my computer actually.
Okay.
Um,